Hey gang, welcome to the Worksheet Solutions Walkthrough for the worksheet, formal charges, hybridization, and resonance. Just a little bit of resonance. If this is your first Worksheet Solutions Walkthrough, what we're going to do is for the worksheet this video is for, which is formal charges, hybridization, and resonance. You've seen the worksheet, you've seen the answers, but maybe you're looking for a deeper explanation. You're in the right place. This video is just going to be me going through the worksheet as efficiently as possible and maybe providing an explanation that's a little bit deeper than the PDF solutions. So let's go. All right, brave geochemists, let's get started. So in problem one, we do something that I've seen very often on exams. In the first exam, you might have a giant molecule like this, and all you're tasked to do is label the hybridization of each molecule in the structure that's given to you. So we're going to do that, and then as a follow-up question, we have two sets of red asterisk atoms here. On the worksheet, they're just black, but what we're going to do after that, and I'm going to provide a little bit more detail in this video than I did on the worksheet. We're going to draw the molecular orbital diagram, the molecular orbital overlap of this oxygen, that carbon, and then this carbon and that hydrogen, okay? So let's go through and label the hybridization of each atom in this molecule. So remember, when we're doing hybridization, right, we understand, we already know the bonding theory. We know that when an atom needs to go to make those head-to-head sigma bonds, hybrid orbitals need to be created, right? We put the orbitals we need in our molecular blender, we blend them up, and then if we do need any p orbitals for pi bonds, then we set those aside, and they're unhybridized. But when we're on test day, we use our shortcut, right? We look at each atom, we count the bonding areas, which really tells us how many sigma bonds are we making, and we can get our hybridization very quickly. So starting right here, if we look at this carbon right here, what's not shown is the bond to hydrogen right there. So really, this carbon has two bonding areas, one here and one here in the triple bond. This carbon is sp hybridized. I'm going to leave this hydrogen off here because I didn't label it in the worksheet. Anyways, this carbon, also one bonding area right here for the triple bond, one sigma bond there, and then one bond here. This carbon is also sp, because remember, when we have these orbitals to work with, s, p, p, and p, because that is what carbon's valence brings to the table. At least in the, atoms in the second row of the periodic table bring the table twice. So this carbonyl carbon right here, you can see there's a bonding area, and a bonding area. So this carbon right here is sp2 hybridized because there were three bonding areas, spp. This oxygen up here, one lone pairs count as bonding areas, 1, 2, 3, also sp2. This carbon, 1, 2, 3, sp2. This carbon right here, there's a hydrogen we're not drawing, 1, 2, 3, sp2. This carbon right here, 1, 2, 3, also sp2, because right, we needed three orbitals, s, p, and p. This carbon right here, 1, 2, 3, 4. This carbon, sp3. Four bonding areas, we need sp, sp3. There are three implied hydrogens here, three implied hydrogens here, three implied hydrogens here. These carbons are all equivalent, so if I just look at one, the hybridization is the same for the rest. 1, 2, 3, 4, sp3, sp3, and sp3. Okay? This carbon right here, we have a hydrogen that we don't have drawn explicitly. 1, 2, and 3, also sp2. Same deal up here. I think you're seeing a pattern. sp2, sp2. This carbon up here has a hydrogen we're not drawing, sp3. This oxygen up here, two lone pairs we haven't drawn in. 1, 2, 3, and then a fourth bond to that hydrogen, sp3 on that oxygen. And just for fun, this hydrogen right here only has one bonding area. It has an S hybridization. That's it. It's just S. This carbon right here has a bond right here that we haven't drawn to hydrogen. 1, 2, 3, sp2. I think I can go a little faster now. sp2, sp, sp, sp3. Three bonding areas, sp2. 1, 2, 3, sp2. And for flashiness, for show, hydrogen, one bonding area, just S. Okay, so labeled all the hybridizations with ease without breaking a sweat, except I might be a little sweaty because my apartment is hot. However, let's tackle our next problem. I'm going to draw a line right here. We'll do this first, and then I'll do that here, and then I'll do this right here. So we want to zone in on this carbon and that hydrogen. So what I want to do is carbon here, hydrogen here, and all we need to do is just show them what kind of orbital overlap is going on there. So clearly we just have a single bond. We have a sigma bond, right? Sigma bonds are the head-to-head overlap. So no pi bonds, just sigma bonds present. So really, I have this orbital coming from carbon, I have this orbital coming from hydrogen, and I even drew them this way on purpose because hydrogen just brings an s orbital to the table. They're spherical. And there's one electron in it. Because in the bond, right, hydrogen brings an electron to the table, carbon brings an electron to the table. And I'll also put one in here. Now, I can label this orbital as S. And I'm going to draw a little arrow to it. Arrow's unnecessary, I'm just trying to be very explicit. Now, remember here, what's carbon's hybridization? What kind of orbital did it bring to the table for the sigma bond, the head-to-head overlap? Well, an sp2 orbital, right? That's why I went through the trouble of trying to figure that out. Okay? So there we go. We've done it for carbon and hydrogen. A very simple example. Things are going to get a little bit more interesting in this next pair. So I have carbon and an oxygen. So we're going to do a C. We're going to do an O. There's a double bond here, so we have one sigma and one pi. So we'll have to draw both of those. So let's do the sigma first, the head-to-head orbital overlap. So these carbon and oxygen are both sp2. So for their sigma bonds, they are bringing, I didn't really draw that true, they should kind of look the same, and of course I'm not the best artist or the best at holding markers. So one electron in each. These are sp2 orbitals. So I'll just I'll label them both like that. However, we have something else going on. We have a pi bond, and remember, a pi bond is a set of unhybridized p orbitals that are parallel to one another, and there is an electron in each of those. So you can see that there's some type of like parallel interaction. It's not as strong as a sigma because there's no head-to-head overlap, but there's a force, a bonding force, between these parallel unhybridized p orbitals. And remember, we can label them, they're just p orbitals. No hybridization, just p. Okay? So that takes care of problem 1. On to problem 2. Okay, gang, so up top, we're going to hit problem 2 first, and then problem 3, and then chug right along. Okay, so in problem 2, we are tasked with taking the structures as they're given to us in molecular formula like this and make it bond line. But we need to make sure that we respect the geometry of the structure based on the bonds and the hybridization that are being, that are present, as well as any charges if they're present, which if you can look in letters B and C, there are some charges. Okay, so in an A, and I kind of want to slap myself on the wrist for this, if we take a look, right, we have a CH2, a C, and a CH2, like this, 3 carbons. So to make sure that this works in bond line, right here, this carbon, all the carbons need 4 bonds, right? So if this carbon has 2 bonds to hydrogen, where are the other 2 bonds for it? Well, it's a double bond between this central carbon and the carbon on the right. Well, if you look over here, we have the same situation. On this terminal carbon, terminal meaning end, we have 2 bonds to hydrogen and 2 bonds in the middle. So this carbon right here, if I'll expand this, we have a situation like this. It almost looks like carbon dioxide, where you have a C and then 2 things on the end with 2 bonds. Now, I messed this up a little bit in the solution. Should have respected the geometry a bit more. But these carbons right here, they are sp2 because there's 2 bonds to hydrogen and then 1 right there. So 3 bonding areas. sp2, sp2, and then the central carbon is sp. Well, if you've looked at the VSAPR video, this is linear geometry when you have 2 bonding areas. We have 180 degrees right here. So the geometry about this carbon should be linear. So if we translate this to bond line, what this really should look like, and it's going to look so silly, is this. We have a carbon right in the middle. I'm going to dot it just to signify that you know that there's a carbon in the middle, and these 2 carbons on the end, since they are sp2, they are trigonal planar in geometry, which means the bond angle is there. So again, you didn't have to do this, but about this carbon we have 180-degree bond angles, and right here we have 120, 120, and 120. And it's the same on the other side over there. So I drew this a little bit more bent in my solution, but I just wanted to make sure this is wrong. I just wanted to make sure you didn't check the solution and think to yourself, where's that middle carbon? So yeah, this is how we take the molecular formula up here and make it bond line. Okay, so moving right along. How can we translate this? Well, we have 3 carbons right here. So you can see this carbon right here has 1 bond going this way and 3 going this way. So again, we have another linear situation because this is sp in hybridization. And I'm now realizing I've made a terrible mistake. Oh, I left a carbon off. I apologize for that. There's an extra C. There we go. I was about to say I broke the octet rule. So if you saw it before, I apologize. Just didn't copy it correctly from the paper. So we have linear geometry here and here, as well as here and here. So I will just draw this triple bond first. So I always like to draw triple bonds first, and then I know I can take care of this by doing this. This is a CH3, so I don't have to do anything. I've taken care of these 2 carbons. Now if I work off this carbon, I have 1 more bond. And there are 2 H's, and I see a lone pair because I need to get a negative charge on this carbon. I need to reflect that a carbanion exists, right? Negative carbon, anion. So if I give a lone pair to this carbon right here, that means 1, 2, 3, 4, 5. It has a full octet because 2, 4, 6, 8. But by giving it the lone pair, it has a negative formal charge. Let me clean some of that up. That is how we would translate this from molecular form to bond line. Moving on. So if we look here, kind of the one thing we have going on is the double bond right here. So I can take care of these 2. I have 1, 2, 3, 4 carbons in my chain. If I draw them like this, I don't have to worry about any linear geometry being reflected. I just need to make sure that I include a double bond right here. That takes care of that. However, the last thing is that this carbon right here is a positive, it is a carbocation, a carbon cation. I just need to make sure I reflect the fact that it has 1 less bond than 4, because you can see the 1 bond to carbon, the 2 bonds to hydrogen. I don't have to draw these, but just for clarity, you can see that is how it exists. So I'm going to erase that. So that is problem 2. More of a shout out of going from molecular form to bond line, but throwing in formal charges as well as respecting geometry as well. So now in problem 3, it's really just go through the structure, and yeah, it was kind of annoying because I'm sure you're getting used to bond line by now, and trust me, in just a few weeks you'll even wonder why you may have wanted to see structures in this form at all. But just go through. We need to just find any formal charges if they exist. So this carbon looks fine, 4 bonds. If we look at this carbon right here, I see 1, 2, 3 bonds. Not a full lot, it comes in with 4 valence electrons. It's in control of 1, 2, 3. That is a positive charge on that carbon. This carbon is good. This carbon's good. 1, 2, 3, 4. That carbon's good. Carbon's good. Carbon's good. This carbon's good. That carbon's good. This carbon's good. Let's check down here. That carbon looks okay. This carbon looks 1, 2, 3, 4. However, let's look at this oxygen right here. Now there's definitely a lone pair that I did not draw, which is not uncommon to see. 1, 2, 3, 4, 5. Well, oxygen comes in with 6. So this oxygen has a +1 formal charge. Okay? So now let's keep going. So we said these are all good. This carbon looks okay. So now we get to, and I'm sorry, gang, I forgot to put an H right here. Okay? This carbon's good. Now if we look at this oxygen up here, didn't draw in these lone pairs, at least right here. So we can see it's in control of 7 electrons. This oxygen has a negative charge. And then if we look at this right here, and I should have filled that in as well, I apologize. We see 1, 2, 3, 4, 5. This carbon is also negative as well. So these are the charges, the positive cation here, the positive oxygen here, the negative oxygen here, and the negative carbanion on the end of the structure. Okay, sorry about the little mishaps as far as translating things from paper to board. Okay, so I'll erase this and we'll move on to the next problem. Okay gang, problem 4, 2 problems. We're gonna do one at a time and then it's quits for this worksheet video walkthrough. Sorry, still getting used to saying that instead of, welcome to another video here on jOeCHEM. Okay, so if we look at, we have the sulfate ion. So this is, you know, the second conjugate base of H2SO4 after H plus is given twice. So let's draw some resonance. That's what we need to do, draw all the unique resonance hybrids. So what do we do? So I just drew the Lewis structure. It's probably one you should be very familiar with. It's very easy. It kind of looks, you know, there's a lot of symmetry. So let's start our double-headed arrow, say, hey, look at me, I'm drawing resonance. So the first move I'm going to make is I'm going to, you know, remember, when we move 2 electrons, we use a double-headed arrow. So I'm going to make a double bond from that lone pair right there. Sulfur, if you're wondering, it's in the 3rd row of the periodic table. It has an expanded octet, so even though we're well over the octet rule right now, that's okay. But in this resonance move, I'm going to make a double bond, and I'm just going to go ahead and bounce up a double bond as a lone pair. I can do that on this oxygen. Now there's absolutely no, if you're wondering how I produced the structures, if there's a certain order to it, absolutely not. It doesn't matter if you started in a different way, as long as we ended with the same amount of structures at the end, okay? So let me just trust my arrows. Sulfur is still the central atom. I now have an oxygen up top. I have a double bond over to the right with 2 lone pairs. Didn't touch that oxygen. Did not touch this oxygen. So let me fill in my charges. That negative charge is still there. I'm going to switch over here now. And now I have a negative charge up top. Right, because 1, 2, 3, 4, 5, 6, 7 for that oxygen. And this oxygen is now neutral because 1, 2, 3, 4, 5, 6. Okay, so let's keep going. Double-headed arrow. What I'll do now is I will reform this double bond. No, I won't. Sorry. I will form a double bond. You know what? I will do that. Sorry, haven't drawn this one in a little bit. I'll reform the double bond right there, and I'll do something different. I will kick up electrons onto that oxygen. Double bond up top. 2 electrons right there. I'm just going to move my arrow to give me some space. Didn't touch this oxygen over here at all. I now have an oxygen down here with 3 lone pairs. Didn't touch this oxygen at all. Okay, so I labeled the negative charge already, but now I have the negative charge down here. So what I can go ahead and do is I need to form a double bond where I haven't done it before. So what I can go ahead and do is swing these down and then kick these up. This problem is very much about just figuring out what all the combinations are to include all the various resonance structures. So double-headed arrow. I'm going to go and draw this oxygen like this just so I can go left to right. So I have a double bond right there. Sulfur is the central atom. Didn't touch this oxygen up top. I have an oxygen over here. And I still have that oxygen at the bottom with the 3 lone pairs. And I think you can pick up the pattern. Negative charge right here, I also didn't touch it. Negative charge over here as well. So keeping it rolling along. I'll draw another double-headed arrow. And I am going to cheat at my sheet just because I'm losing track of what I have drawn and what I have not drawn. So what I'm going to go ahead and do is we have not had a double bond down here for a little bit, so let's swing these down right here. And as I do that, I will actually kick these up. So sulfur in the middle, oxygen up top with 3 lone pairs, oxygen over here with 3 lone pairs, didn't touch that, double bond, 2 lone pairs, 2 lone pairs, negative charge, negative charge. Let me just verify, let me just check that I didn't do that yet. Yep, that's a unique structure. We just have 2 more, at least my paper down below tells me. So the next thing I'm going to do is I'm going to swing these down and then kick these up. Give that oxygen at the bottom a charge again. Double bond right here, 2 lone pairs. Oxygen up top with 3 lone pairs. And now have, let me just make, hold on, sorry gang, let me just make sure that I'm not drawing a duplicate. Yes, this looks okay. Yep, okay. Yep, sorry, just it looks different on my paper than the layout, that is. So, I have an oxygen with 3 lone pairs right here. And then I have double bond over here. Oh, that is, yeah, that's the result. So wait, let's see. 1, 2, 3, 4, 5, 6, that's the end. 1, 2, 3, 4, 5, 6. Okay, cool. Yeah, so in this move, we actually end up in the original structure. We finally got back to where we started. Oh, it just looks a little bit different, actually. Sorry. Oh, I apologize. There's just a lot of similarity here. So all this was an exercise in doing was I just wanted to make sure that now that we have, officially talked about formal charges, I just wanted to, we bring resonance into the forefront and just have a video where we just did a structure like this, where, the central atom has an expanded octet. There's a lot of similarity, but remember, right, even though there's a lot of symmetry going on, these are 4 different oxygen atoms, right? Yes, they are all equivalent, but they are 4 different ones attached to this sulfur. So if you just do your accounting and you do a little bit of a better job than I did at keeping sure, keeping track of which structure you've drawn already, go through all the combinations, you end up with all of the resonance hybrids for sulfate, which is 6 structures, okay? So let me erase this. We will do the nitrobenzene, which don't worry that's just the common name for that structure, and then we'll call it a video. Okay, gang, last example on problem 4. So if we look at this structure, we have a compound called nitrobenzene. And when we talk about functional groups, you'll see that an NO2 is a nitro group, and we will actually draw this exact same resonance if you're still rocking with me in jOeCHEM 2 when we get to the benzene unit. But for now, we're doing resonance. So if we take a look at this right here, the first, I wanted to show this example because I think it shows very unique resonance, and if you can handle this, you can handle pretty much anything. So let's draw our double-headed arrow saying, hey, look at us, we're drawing resonance. And this move is a bit weird, but hopefully this may sit well with you if I explain it this way. So if we look at the structure, we have this positive nitrogen up there. So since that is directly attached to a ring full of double bonds, right, and double bonds have 4 electrons versus 2 in a single bond, it makes sense to move electrons towards that nitrogen. So in my first resonance move, I'm going to take this double bond and I'm actually going to make it a double bond over here. So instead of this carbon and this carbon having a double bond, it's going to be this carbon and this nitrogen having a double bond. Now remember, we just worked with sulfur, but that was in the 3rd row of the periodic table, and we could expand the octet. Now we're back in 2nd row territory with carbon, nitrogen, and oxygen. So if I do nothing, I'm going to kind of screw nitrogen and break the octet rule. But luckily, I can take one of the bonds in the oxygen-nitrogen double bond and give it completely to oxygen, right? So remember, I'm using double-headed arrows to signify both electrons in this double bond are going to go here, and then both electrons in that double bond are going to go there. So if I trust my arrows, which you always should, I didn't touch the double bond here or here. So I always like to fill in what I haven't touched because, let's build up that confidence before we draw the whole thing. Then I have a double bond here. I have a nitrogen. I didn't touch this oxygen up here, so I'm going to automatically just slap that negative charge right there. And then I have my oxygen way up here, which hopefully you can see. So we started neutral, right? Positive, negative. We need to end neutral because remember, resonance just rearranges electrons. It doesn't add or subtract anything. So if we look at this oxygen, my oh my, it doesn't look just like that oxygen. And if we wanted to verify, it's in control of 7 electrons because 1, 2, 3, 4, 5, 6, 7. Negative charge. Okay? Now, we are not neutral here, right? I need to fill in some other things. So if we look at nitrogen, nitrogen still has the same setup. A double bonding area and then 2 single bonds. So 1, 2, 3, 4. Nitrogen still has a positive charge. However, we're not still neutral, right? We still have another charge to label. If you can see this double bond moving right here, this carbon is still a part of it here and here. However, this carbon is a little SOL, right? It lost out on electrons. So this carbon, which has a hydrogen we haven't drawn, is now a carbocation. So if you can see, now we're neutral. Big resonance move, a little bit weird taking electrons out of the ring, and we have 2 sets of charges offsetting each other, but now we're kind of out of the woods because the remaining resonance we need to draw is, classic ring around the rosy type deal. So what we can do next is I'm just going to keep moving double bonds towards that carbocation. So I'm going to take this double bond and I'm going to move it right here to make it a bond between this carbon and this carbon, which means this carbon, the positive charge is just going to jump from here to there. So we just redraw it. Redrawing takes the most effort, in my opinion. Bond is here now. Didn't touch this. Didn't touch anything up here, so we can just completely and mindlessly redraw it. Okay, so remember the carbon here now is a part of this bond, and it's this carbon that's losing out, so the positive charge is here now. And we can do resonance one more time. Let me draw the arrow going this way. I can, again, move this double bond down here, meaning the charge is going to go from here up to here. I still have exactly what's going on up top. Again, I'm going to fill it in kind of mindlessly since nothing changed. Double bond here, and double bond here, and the charge is now here. Whew. All right, gang, thank you for going on this formal charge resonance soiree with me. I hope the worksheet has been informative. I hope this walkthrough gave you maybe some extra clarity that you were looking for. I appreciate you paying the amount of money you did to watch these video walkthroughs, these worksheet walkthroughs. I appreciate you supporting jOeCHEM. I appreciate you bringing me along the ride, your ride, for organic mastery. And I hope I will see you all in the next video.